Hello. What we're going to do today is we're going to solve a myriad of integral problems taken from section 6.2 of Stewart, Essential Calculus, Early Transcendentals. These will be taken in just roughly the order of difficulty, sort of. Well, we'll see. We'll see where we're going to go. And I'm going to go ahead and start the screen share, and we'll get started. All right. So the very first thing, now of course it helps to be able to write the problem in readable form. This is sine of 5 fifth power x. It's a definite integral going from 0 to pi over 2. So we're going to have to do some definite integration here. Shouldn't be a big deal because this is sine to an odd power. This is sine to an odd power. We can do as follows. We can write this out. We can write this now as sine 4x, sine of x, dx. And the understanding here is that this is going to be set up to be our du. So we're looking for a u equal cosine x sort of thing. And I should say this is almost, because the derivative of cosine is in fact negative sine. That's all right. We can do something about that. This is sine to an even power. That can therefore be transformed as follows. This is sine squared x squared sine of x dx. Now you might say, well, okay, that's sine squared. Well, we're going to use our circle identity here. Write this as 1 minus cosine squared x squared sine of x dx. Now we could square this out. It's my recommendation that we instead make the substitution to this and do the substitution as follows. U equals cosine of x. Du is minus sine of x. Dx, or minus du is sine of x dx. So this is transformed. Take the minus sign. 1 minus u squared du. Now we do have some limits to worry about. That should not be a problem because let's just go ahead and take a look here. Where x is 0, u is cosine of 0, which is 1. On the other hand, upper limit, where x is pi over 2, u is cosine of pi over 2, which is 0. Like so. Now notice this negative works very, very well for us because this negative can invert these signs here. And I could just say, just finish the integral on your own, but this is a polynomial integral. And the integral works out very easily. Watch me blow it. Now this is a definite integral, so we've already changed the limits, so there's no back changing. And that works out to be 1 minus 2/3 plus 1/5. And the arithmetic bores me, so I'll stop here. I think you can handle it from there. The key, though, is recognizing this is sine to the 5th power. That leaves you something to use as a du. So we have a sine to a power, cosine to a power. If it's an odd power, peel off one of those and use that as your du and switch it to the other one. Next, we have a cotangent to the fifth. I have a hard time running with fives. That's a 5 there. Sine to the fourth dt. Now, if you're scratching your head, say we have not done a cotangent in the sine, that's okay. Let's revert to first principles and see where that gives us. Well, cotangent is cosine to the fifth, sine to the fifth, sine to the fourth. Okay? Now that kind of looks kind of like, well, what are we going to do here? Because one of these will cancel. The sine to the fourth, well, we could try canceling it all the way out. So we now have sine of t, because one of those cancels. I still have a cosine of to the fifth dt. Now that's kind of looks kind of like, well, what you gonna do? My recommendation here is we do have the cosine to the fifth. We do have a sine down here. So one way to proceed, and there may be other ways, this is a way that I think might prove fruitful. Now notice I said might, because you're not, well, maybe you can be 100% sure, but it's hard to be 100% sure for the first time. Let's use one of these cosines. Then we have a cosine, and we have a sine down here. Now it may look like we haven't done much, but I think it wouldn't hurt for us to think about that as our du. This would be u is sine of t. Now the cosine of the fourth, well, we can do something about that. This is going to be what we're working toward. We haven't made the substitution yet. This could be a cosine squared of t squared sine of t cosine t dt. We're off and running now, because that's now 1 minus sine squared of t squared sine of t cosine t dt. Now we can use our u equals sine of t. With that substitution, we said that's going to be a du. This reverts to 1 minus x squared, or u squared. Let's make that a u. So it's now going to be 1 minus 2u squared plus u to the fourth all over u. And that's now a fairly simple integral to do. Now we're pretty much home. Log absolute u minus u squared plus u to the fourth over 4 plus c. But that's not exactly how we had the problem originally. Originally, it's u is sine t. So the actual answer is going to be natural log of absolute sine t minus sine squared t plus sine fourth t over 4 plus c. Okay? But you see, the key here is that we actually had to do some manipulation, and then once use that principle right here to let that work. Now this one might look tricky. What we notice is we have a 2x in the argument here. We only have a solitary x. Now there is an optional video about how to go about doing sines and cosines of different powers using angle addition formulas, but this is in fact a cosine squared. And we did have one thing that's going to help us. It's the double diagonal formula. We replace this by 1/2 plus 1/2 cosine of 2x sine of 2x dx. Now that works okay, doesn't it? Now we're off and running. Now, when we actually integrate this integral right here, the sine of 2x, we can just do directly. This one here is going to be a u substitution, and you have a choice. I recommend letting u equal sine of 2x, du equaling 2 cosine 2x. So let's just do these separately. The very first interval here would be minus 1/2 times 1/2 cosine of 2x, because the derivative of here, the derivative of cosine of 2x is minus 2 sine of 2x, so that accounts for the negative sign. In this case, I'm going to let this be your u here, and your du will be this. Now, of course, if du almost, because the real du is going to be 2 cosine 2x, so this works out to be 1/4 sine squared 2x over 2, because this is really a u squared 1/2 du, and then you have another half. So this works out to be minus 1/4 plus 1/8 and plus c. Okay? That didn't look out to be too bad, did it? Now we got a challenge. We have a cosine x minus 1. Now, I want to say about this particular problem, there are reasonable things to try. But this is a video, and I don't wish to waste your time here, but it might not hurt to try your hand at some of these. One of the things, though, I think will help us out is that this cosine of x minus 1, there is a way of resolving it. And if you remember what that is, you remember something like this. So let's recall. Recall that sine squared of x is 1/2 minus 1/2 cosine of 2x. So if you multiply by negative 1, multiply by 2, and then make the substitution, make the substitution 2x equal t. This is minus 2 sine squared t over 2. Do you see what to do now? So this whole interval, it's not really a substitution, it's a trig identity, is now equal to dx minus 2 sine squared t over 2, which is basically minus 1/2 integral of cosecant squared of t over 2, x, darn it, did it again. And remember, there's an actual antiderivative here. And the antiderivative of the derivative of cotangent is minus cosecant squared, and we have that right there. So we just recall. So what we have here, using this fact, using that we have negative cosecant squared, this is actually going to be negative 1/2 cotangent x over 2, and then we, sorry, there's no negative anymore because the negative is there, and then we multiply this by 2, and this is what we get. Okay. Kind of an interesting problem here. But it turns out this is really just trig identity. That the negative takes care of itself. And yeah, that's correct. So. Now this problem here. We have an x cubed and its definite integral. And if you look at the definite integral, this really looks like a mission for the tangent function. So I might try letting x equal 2 tangent of t. So this now becomes, well, if you cube it, it's going to be 8 tangent cubed t. This is going to be the square root. And this is going to be 4 tangent squared t plus 4. And I get another 2 secant squared t dt and the dx. The 2, so this turns out to be 16. Now I haven't done anything with the limits yet, so let's just put little boxes here to indicate we want to work on those in just a second. So now I have a tangent cubed. This is going to be a 2 secant squared t. Now in the range in question, secant is going to be positive. So I've got this 2 right here, right here. 4, sorry, it's still a 4 underneath. So the 8 times the 2 is the 16, so that's 2's taken care of. Still got that 4 out here. And then now I'm going to go ahead and do something with that 4. Take it outside the radical, it becomes a 2. I still haven't done my limits yet. So I have a tangent cubed t, secant cubed t dt. Now let's do a few limits here. If x is 0, t is 0, because tangent is 0, 0. If x is 2, then tangent of t is 1, so we're going to have t equal pi over 4. Now we've gotten this completely done over. And notice secant cubed is odd, well, odd power. So that's not going to help me too much. Oh, yes, yes, yes. This is correct, but I think probably the best thing to do is to pull a tangent secant out. And then what we have left over is a tangent squared secant squared. Yeah, this is going to work. The reason that works is we now are going to set up a U substitution, and we're going to convert the tangent squared. Tangent squared plus 1 is secant squared, so it's going to be secant squared minus 1. And what we're really setting up right here is really setting up this to be your du for another substitution integral. So this turns out to be 32, 0 pi over 4, secant 4, there's a t there, minus secant squared t, tangent t, secant t, et, and we're basically on our way to being done. I might just add another clean piece of paper because I have problems written on the others. This is not going to be much of a finish though, because this is really u to the 4th minus u squared du. So that's going to turn out to be equals to 32 secant to the 5th t over 5 minus secant cubed t over 3, evaluated between 0 and pi over 4. And we know now it's in 32. We plug in the pi over 4, we basically get root 2 to the 5th over 5 minus root 2, 3 over 3, subtract 1/5 minus 1/3. And I'll let you work out the numbers there. We've sort of done the hard part. Next, sort of going through the motions here, we're down to 3 more problems. This one, t squared minus 16t squared. Why don't we try, well, we can try a couple things. I'll go ahead and try t equal 4 secant, secant x. dt is 4 secant x tangent x. So let's see what this integral is transformed to. We have a 4 secant x tan x top. Bottom, we have 16 secant squared x. And then on the bottom, we have 16 secant squared x minus 16. The 16 outside turns into a 4. That 4 cancels that, so this is a 1 over 16. This 4 is going to cancel that 4. We have a secant x tangent x, secant squared x, and this is going to be the square root of tangent squared x. Assuming we're in the right range, that becomes cancellation. This is actually going to work out pretty easily right here because secant divided by secant squared is just 1 over secant, which is another way of saying it's just plain old cosine. But as usual, we understand that our x is really going to be, remember, our x equals arc secant t over 4. And we're going to take a tangent, we're going to take a sine of that. Well, remember secant is going to be hypotenuse over adjacent. Pythagorean theorem says that's going to be t squared minus 16. And then sine of this angle is going to be this over hypotenuse. So the square root of t squared minus 16 all over the hypotenuse. Okay. Let's go through this one here. Now this one here is actually a lot easier than you might think. The reason for it is that if you do the first u substitution, this really becomes square root of 1 plus u squared, and that's just a du. Now we ought to change the limits here. So if t is 0, u is 0. T is pi over 2, u is 1. So this is just this interval right here. And we can do this a couple of different ways. You can use hyperbolic trig functions, which might be a cool way to go. And I might just use tangent here. So we get the square root of 1 plus tangent squared t, secant squared t dt. Now if t is in fact, well, if u is 0, t is 0. If u is 1, t is pi over 4, because tangent of pi over 4 is 1. I'm back to a t again. Well, doesn't matter. This is actually correct. That's just going to be the square root of secant squared, or secant. And since it's a definite integral, we can keep it like that. The antiderivative is secant t plus tangent t. Evaluated between 0 and pi over 4. When you plug in a 0 here, you get 1 plus 0, but log of 1 is 0. You plug in pi over 4, you get log the square root of 2 plus 1. How about that? Finally, let's see how this one goes. The bottom looks gnarly. So what you're going to do? Well, completing a square is sometimes a good idea. So if we just do the completion of a square, we have a minus 2x plus a 1. So take half of 2 is 1 squared, you get 1. You still have 1 left over. So this is now x squared plus 1. There we have an x plus 1 squared plus 1. You might be saying, well, what do you do with that? Well, my recommendation is that you do this and you can try something. If you let it u equal x plus 1, then, well, that might help, it might not. What I would do is I treat this as a double substitution. I would write it like this. Have to be careful here. Now this one is not going to be too bad. To do the second integral, that's kind of where, actually you can do them both that way, I think. Here, if you let u equal x plus 1, du is just dx, because it's just a switch. So we have here 1 over u squared plus 1 squared. We know what that one's going to be. So it's going to be an arctangent type of situation. If we do something similar here, well, this one could be an integration by parts. We could try to do it this way as well. Let's try this as a integration by parts. I might regret that. Now this one here, if you let u equal tan theta, du is secant squared theta d theta. This corresponds to secant squared theta. The bottom turns out to be secant to the fourth theta. That's going to be a cosine squared integral there, which is very doable. And you know what? I might, rather than do an integration by parts, I might make the same substitution here. It's sort of going in circles. So here, I'll just go ahead and do the parts. U dv. So this is it. So du is dx. V is basically antiderivative of this. So it's going to be 1/2, because basically what you're doing here is you're taking u equal, when you're finding the antiderivative here, the derivative of this is going to be 2x plus 1. You know, I realize that sort of, you know, this is a bit ham-fisted. I think I prefer a different way. So I'll just go ahead and do it. This is correct. The completion of the square is correct. I think it's probably best just to start it like this. Go back to basics. Okay, yeah, let's go ahead and start it like that again. And let's go ahead and make our substitution as we might. Let's try x plus 1 equal tangent theta. Then dx is secant squared theta d theta. So let's see what we have right here. We have tangent squared theta plus 1 squared, secant squared theta d theta. So good, so far so good. Oh yeah, this is probably going to work better. This is now x is tangent theta minus 1. X squared is tangent squared theta, is tangent theta minus 1 squared. And then you have a 1 here. So you have a then you have a plus 1. Yeah, so that's a correct statement right there. Now notice what happens. This integral, the secant squared, this is going to be a, let's just do this. We get a tangent squared theta plus 2 tangents theta. minus, I'm sorry, plus 1, the top. The bottom, we have secant fourth theta, secant squared theta d theta. And we now have tangent squared theta minus 2 tangent theta plus 2 all divided by secant squared theta. That's actually not as bad as it looks. Okay? Because if we now change this, tangent squared divided by secant squared is really going to be sine squared theta. Why? Because this is sine squared over cosine squared. The bottom is going to be cosine squared and the cosine squareds cancel. This is going to be minus. Now, the two, this is going to be 2. I'm going to write this as sine theta over cosine theta times cosine squared theta plus 2 cosine squared theta. Now we got it. See, I should have done this to begin with instead of trying all the other shenanigans. I'm not going to completely finish the problem yet because this works out to be the sine squared plus cosine squared is 1, and we still have an extra cosine theta. Now we have cosine squared divided by cosine squared minus 2 sine theta cosine theta. Yeah. Let's go ahead and finish the thing up. If you're wondering, sine squared plus cosine squared is a 1, so I still have this extra 1 here. So I now have a 1 plus another cosine squared theta. And then I have this. So now I'll just go ahead and just do it this way. This integrates to theta plus 1/2 theta plus 1/4 sine 2 theta minus, well, this is just a u substitution with u equals sine. But remember what all this was. So remember now to get back, remember sine of 2 theta is 2 sine theta cosine theta. So this is theta plus 1/2, well, 3/2 theta plus 1/2 sine theta cosine theta minus 2 sine squared theta plus c. Now let's just go ahead and do this. Remember what our theta is. It was our arctangent of x plus 1. So that resolves that. Now remember tangent theta being x plus 1, x plus 1, 1. This is square root of x plus 1 squared plus 1. So now sine of that is going to be opposite over hypotenuse. Cosine is going to be adjacent over hypotenuse, and the two hypotenuses, hypoteni, give us that. And then remember sine squared. So it's going to be x plus 1 squared divided by x plus 1 squared plus 1. And there it is. Okay.